Right now, without knowing it, you are moving through space at roughly 600 kilometers every second, pulled towards something vast and mostly hidden, something with no name that quite captures what it is. Welcome to the Sleepy Lab. Tonight, we drift toward one of the quieter mysteries in all of cosmology, a region of the universe so massive it bends the motion of entire galaxies, including our own. We will follow the pull, trace the history of its discovery, and sit with the uncertainty that still surrounds it. If this kind of gentle journey through science helps you sleep, consider subscribing, one sleepy soul at a time. Now, let's begin. Somewhere in the direction of the constellation Centaurus, roughly 250 million light years from where you are lying right now, there is a region of space that does not announce itself. It has no sharp edge, no single blazing center, no obvious marker that would tell you, if you could somehow travel there, that you had arrived somewhere significant. And yet, the Milky Way is moving toward it. Not drifting, exactly. Moving with purpose, or at least, with the quiet inevitability of gravity. About 600 kilometers per second, which sounds enormous, and yet, across the scale of what lies between us and that region, it is something closer to a slow, patient lean. This is the Great Attractor. The story of how we came to know about it begins not with a telescope pointed at something visible, but with a pattern in the unexpected. It was the 1970s. Astronomers were cataloging the velocities of galaxies, measuring how fast they were moving and in which direction. The universe is expanding, and so most galaxies are receding from us. That much was understood. But some galaxies were moving in ways that didn't quite fit the smooth, even expansion the models predicted. There were deviations, subtle ones, but consistent. Galaxies in certain parts of the sky were moving slightly faster than they should have been. Others were moving slightly slower. And when astronomers looked carefully at the pattern of those deviations, they began to see something underneath, a kind of gravitational current, pulling matter across enormous distances toward a common point. Something was out there. Something with enough mass to nudge entire galaxies off the path they would otherwise follow. It took another decade before anyone could say so formally. In 1986, an astronomer named Alan Dressler, working with a group of colleagues who would come to be known informally as the Seven Samurai, published a careful analysis of galaxy motions across a wide region of the sky. They had measured the distances and velocities of hundreds of elliptical galaxies, and they had found, embedded in the data, a coherent flow. Galaxies were streaming, not randomly, not in all directions, but together toward a region in the southern sky. Dressler and his colleagues gave that region a name: the Great Attractor. It was a name chosen for what it did, not for what it was, because what it was remained difficult to say. And here is where the story becomes something quieter than a discovery, something more like a puzzle held gently in both hands. The Great Attractor is not a single object. It is not a black hole of unimaginable size, or a single galaxy so massive it warps everything around it. It is something harder to picture, a broad region of excess mass, spread across hundreds of millions of light years, where matter has gathered more densely than average, and where the combined gravity of countless galaxies, galaxy clusters, and vast quantities of unseen matter creates a pull that reaches across the cosmos. A region, not a thing. A tendency in space, not a destination with coordinates. And then there's the problem of where it sits. The Great Attractor lies almost directly behind the plane of our own galaxy, behind the dense band of dust and gas and stars that makes up the Milky Way's disk. Astronomers call this obscured region the Zone of Avoidance, not because anyone chose to avoid it, but because the interstellar dust there absorbs and scatters visible light so thoroughly that optical telescopes simply cannot see through it. Roughly 20% of the sky is hidden behind this veil, and the Great Attractor sits almost perfectly within it. For years, this meant that the very thing pulling our galaxy through space was also the thing most difficult to observe directly. Astronomers could infer its presence from the motion of galaxies on either side of the obscured zone. They could trace the gravitational current like a river felt, but not seen. But they could not look at it clearly. It was like trying to understand a landscape by watching which way the water flows, without ever being able to see the hills. Infrared and radio telescopes changed this, slowly. Unlike visible light, infrared radiation and radio waves can pass through interstellar dust with far less interference. When astronomers turned these instruments toward the Zone of Avoidance, they began to find what had been hidden: hundreds of galaxies, previously uncatalogued, quietly sitting behind the veil of our own galaxy's disk. The hidden universe behind the obscured zone began, gradually, to come into focus. What they found there was not empty space. Near the heart of the Great Attractor region sits a massive galaxy cluster known as the Norma Cluster, catalogued also as Abell 3627. It is one of the most massive clusters in the nearby universe, a dense gathering of thousands of individual galaxies. Bound together by gravity, their hot intracluster gas glowing in X-ray wavelengths like embers in the dark. The galaxies within it move relative to each other at hundreds of kilometers per second. And yet, from our vantage point, 250 million light-years away, it all appears still. The light we receive from the Norma Cluster left its source roughly 250 million years ago, at a time when the continents of Earth were arranged differently, when the oceans held different creatures, when the first dinosaurs had not yet appeared. That light has been traveling ever since. And the cluster itself, the thing that emitted it, has continued moving, continued evolving, continued pulling matter toward itself across all the time that light was in transit. Observational cosmology is always in this way, a kind of archaeology. We do not see the universe as it is. We see it as it was, layered in time. Each distance a different depth of history. The Great Attractor we observe is the one that existed long ago. What it is now, we can only infer. And so the mystery holds its shape. A region of excess mass, hidden partly behind our own galaxy, inferred first from the quiet deviations in how other galaxies move. Named in 1986 by astronomers patient enough to read the current beneath the surface of the sky. The Milky Way leans toward it still. 600 kilometers per second through the dark, towards something vast and not entirely understood. And you, lying here, are part of that motion, carried along without effort, without awareness, through a universe that does not pause. 10,000 trillion times the mass of our sun. That number is not meant to be grasped. It is meant to be felt. The way you feel the weight of deep water without needing to count the molecules. The Great Attractor is not a star, not a galaxy, not even a single cluster of galaxies. It is a region, a broad, sprawling concentration of mass spanning hundreds of millions of light years, pulling everything within its reach along slow gravitational currents that have been flowing since long before the Earth existed. 10,000 trillion suns, each one a furnace, each one burning quietly in the dark. And all of that, every last burning point of it, gathered into a gravitational presence so deep that galaxies hundreds of millions of light years away cannot help but lean toward it. The Milky Way is one of them. We lean too. And yet, for all its scale, the Great Attractor is one of the harder things in the sky to study. Not because it is distant, though it is. Not because it is faint, though parts of it are. But because of where it sits. Almost directly behind us. Not behind us in the sense of being on the far side of the Earth. Behind us in a deeper sense, hidden behind the plane of our own galaxy. The Milky Way, seen from within, stretches across the sky as a broad band of light and dust and gas. That band is beautiful. It is also, in certain directions, nearly opaque. The dust between the stars scatters and absorbs visible light the way fog absorbs the beam of a distant lamp. Look through enough of it, and the light simply does not arrive. Astronomers call this region the Zone of Avoidance. It is not a place they chose to avoid. It is a place where observation becomes very difficult, where the dust and gas of our own galaxy obscure roughly 20% of the sky from optical telescopes. 20%. A fifth of everything above us, hidden behind the material of our own home. And the Great Attractor sits almost precisely there. It is a quiet irony of our position in the universe, that the thing pulling us most strongly across the largest scales is also the thing most difficult to see. We are drawn towards something we can barely look at directly. We infer its presence the way you might infer a fire in another room, not by seeing the flame, but by feeling the warmth, noticing the way the air moves, watching how others turn toward it. The galaxies around us are the air. Their motions are the warmth. For a long time, the Zone of Avoidance was simply accepted as a limitation, a gap in the map. Astronomers cataloged what they could see and left that band of sky largely blank, not because nothing was there, but because the tools available could not reach through the obscuring veil. Visible light cannot pass through dense interstellar dust, but other wavelengths can. Infrared light, with its longer wavelength, slips through dust more easily than visible light does. Radio waves pass through almost entirely unimpeded. And so, as telescopes sensitive to these wavelengths were developed and refined, astronomers began to turn them toward the Zone of Avoidance, toward the blank band in the map, and look. What they found was not emptiness. It was structure, hidden structure. Galaxies that had been there all along, quietly going about the slow business of existing, simply invisible to the instruments that had been looking in the wrong language. When the first systematic surveys began to penetrate the Zone of Avoidance using infrared and radio observations, the results were striking in their quiet abundance. Hundreds of previously uncatalogued galaxies emerged from behind the veil, not faint smudges at the edge of detection, real galaxies, some of them substantial, some of them clustered together in ways that suggested they were part of the very structure astronomers had been trying to understand. The map had not been wrong, exactly. It had simply been incomplete. And incompleteness, in cosmology, matters enormously. The mass you cannot see still pulls. The galaxies hidden behind the dust of our own galaxy still contribute to the gravitational landscape. They are still there, still moving, still part of the web of forces that shapes how everything, including us, drifts through space. There is something worth sitting with in that thought. The universe does not stop existing where our instruments stop seeing. The blank spaces on the map are not voids. They are places we have not yet learned to read. The Zone of Avoidance was, for decades, a kind of silence in the data. And silence, in science, as in life, does not always mean absence. Sometimes it means the question has not yet been asked in the right way. Infrared telescopes asked it differently. And the answer came back. There is more here than you knew. The Norma Cluster, that dense, massive heart near the core of the Great Attractor region, sits close to the edge of the Zone of Avoidance. It was identified, studied, its X-ray glow mapped, its thousands of member galaxies cataloged. But around it, behind the thicker parts of the dust band, the picture remained uncertain for years. How much mass was truly there? How many galaxies were contributing to the pull? The answers depended on being able to see through something that was, for a long time, nearly opaque. Each new survey that pushed deeper into the zone of avoidance added more pieces, more galaxies, more mass, a clearer sense of the shape of the thing pulling us. And the shape, as it emerged, was not a point, not a single dense object at the center of a gravitational well. It was a region, broad, distributed, a landscape of mass rather than a mountain of it. The Great Attractor is less like a drain and more like a wide, shallow basin, a gravitational low point spread across an enormous volume of space, into which matter flows from all directions along paths that are gentle by cosmic standards, but utterly relentless across cosmic time. Relentless is the right word. 600 kilometers per second sounds fast, and in any human frame of reference, it is beyond imagining. Faster than any object we have ever built, faster than any storm, faster than sound by a factor of nearly 2,000. And yet, measured against the distances involved, it is a drift, a slow lean. The Milky Way will not arrive at the Great Attractor in any meaningful sense. The universe is expanding, and that expansion, accelerating as it is, will, at sufficient distances, outpace even this enormous gravitational pull. The destination recedes even as we move toward it. But the motion is real. The pull is real. And the hidden mass behind the zone of avoidance, those hundreds of galaxies that emerged from the dust when we learned to look differently, is part of what makes it real, part of what tips the balance, part of what bends the path of the Milky Way and Andromeda and all the galaxies of Laniakea along their long, slow arcs through the dark. We are moving through a universe that is mostly hidden from us. Not hidden by distance alone, hidden by dust, by wavelength, by the limitations of the instruments we have built so far, by the simple fact that we are embedded inside the very structure we are trying to map, like a reader trying to understand a book from inside one of its sentences. And still, slowly, the picture fills in. Galaxy by galaxy, emerging from behind the veil. Each one a quiet confirmation that the universe is larger and more structured and more present than the silence suggested. At the heart of all that motion, there is a place, not a point, not a single object you could name or photograph cleanly, but a region, dense, ancient, and immense, that sits near the core of everything we have been describing. That place is the Norma Cluster, known also by its catalog name, Abel 3627. It is one of the most massive galaxy clusters in the nearby universe. And when astronomers say nearby, they mean it only in the loosest cosmic sense. The Norma Cluster lies roughly 250 million light-years away, a distance so large it resists any honest attempt at comparison. And yet, in the context of the observable universe, which stretches tens of billions of light-years in every direction, 250 million light-years is, in a quiet way, close. Close enough that its gravity reaches us. Close enough that it bends our path. The Norma Cluster sits near the gravitational core of the Great Attractor region, not as a single source of all that pull, but as its densest, most concentrated expression. If the Great Attractor is a broad basin of excess mass, then the Norma Cluster is something like its deepest point, the place where the basin floor drops furthest from the rim, and it is vast. Within the Norma Cluster, thousands of individual galaxies are bound together by gravity, not loosely associated, not drifting in the same general direction by coincidence, bound, the way objects are bound when they cannot escape, when the gravitational well they share is deep enough to hold them across hundreds of millions of years. Thousands of galaxies. Each one a structure containing hundreds of billions of stars. Each one a world of its own, with its own history of formation and collision and slow transformation, and all of them gathered here in this one region of space, held together by something invisible and patient and enormously strong. The galaxies within the Norma Cluster are not still. They move relative to one another at speeds of hundreds of kilometers per second, not drifting, not coasting, moving with a kind of restless energy that reflects the depth of the gravitational well they inhabit. The faster the galaxies move within a cluster, the deeper the well must be to contain them. It is one of the ways astronomers measure mass they cannot see directly, by watching how fast things move inside it. And in the Norma Cluster, things move fast. That motion is not chaotic. Exactly. It is the motion of objects in orbit, in infall, in the long, slow process of a cluster still assembling itself, still drawing in galaxies from the surrounding filaments, still deepening its own gravitational hold on the region around it. A cluster like this does not reach a final state. It continues to grow, to accrete, to pull more mass toward its center across timescales that dwarf anything we can hold in mind. But there is another way to see the depth of the Norma Cluster's gravitational well, and it does not require watching galaxies move at all. Between the galaxies in a cluster like this, in the spaces that look, at first, like emptiness, there is gas. Not the thin, cold gas of interstellar space. Something far more extreme. Intracluster gas, heated by the same gravitational compression that holds the cluster together, reaching temperatures of tens of millions of degrees. Gas so hot that it does not emit visible light at all. It glows in X-ray wavelengths, a kind of light the human eye cannot perceive, that passes through ordinary telescopes without leaving a trace. That requires instruments specifically designed to catch it. When X-ray observatories turn toward the Norma Cluster, they find it glowing, not with the soft light of stars, with the hard, high-energy radiation of gas that has been compressed and heated to temperatures that have no analog in ordinary experience. That glow is not incidental. It is a map, a thermal portrait of the gravitational well itself, deeper where the gas is hotter and denser, shallower toward the edges where the cluster's hold begins to loosen. The X-ray glow of the Norma Cluster is, in a sense, the great attractor making itself visible. For decades, this region was hidden, tucked behind the zone of avoidance, obscured by the dust and gas of our own galaxy's plane. It exerted its pull without revealing its face. Astronomers knew something was there. The motions of galaxies told them so. The deviations in velocity that could not be explained by anything visible. But the source remained out of reach, behind the veil. Infrared light helped. Radio waves helped. Slowly, the hidden galaxies emerged. Hundreds of them, cataloged for the first time, added to the map. And among them, the Norma Cluster came into focus. Not all at once, not cleanly, but gradually, the way a shape resolves out of fog when you have been patient enough to wait. What emerged was not a mystery solved so much as a mystery clarified. Because the Norma Cluster, massive as it is, does not fully account for the pull. The Great Attractor region is broader than any single cluster. The mass is distributed across hundreds of millions of light years, spread through filaments and smaller clusters, and the dark matter scaffolding that underlies all of it. The Norma Cluster is the densest node in that structure, the brightest point in the X-ray sky of that region, but it is part of something larger than itself. And that larger thing is part of something larger still. The Norma Cluster sits within the Great Attractor region, which sits within the Hydra-Centaurus supercluster, which is itself a lobe of Laniakea, that vast structure of 100 million billion suns, flowing inward along its gravitational streams. Every scale contains another scale. Every structure is embedded in a larger one. The Norma Cluster is a center, but not the center. A deep point, but not the deepest. There is something quietly humbling about that. We spent decades trying to find the source of our motion, the thing pulling the Milky Way and its neighbors along their long arcs through the dark. And when we finally looked through the dust and found it, we found not a single answer, but a nested series of them. A cluster inside a region, inside a supercluster, inside a web of filaments that stretches across the observable universe. Each answer opening onto a larger question. The Norma Cluster is real. Its gravity is real. The thousands of galaxies bound within it, moving at hundreds of kilometers per second through gas hot enough to glow in X-rays. All of that is real and present and happening right now, 250 million light-years away in the direction of Centaurus. And the light we used to see it left its source 250 million years ago, before the first flowering plants, before the first dinosaurs set foot on land. The Norma Cluster we observe is the Norma Cluster as it was, not as it is. By the time that light reaches our instruments, the cluster itself has continued along its own path, deeper into its own future, further along the gravitational flows that shape this corner of the universe. We are always looking backward. Every observation is a memory. Every image is a record of something that no longer exists in quite that form. The universe we see is the universe as it was, layered in time, each distance corresponding to a different moment in the past, so that to look outward is always, also, to look inward toward an earlier version of everything. The Norma Cluster glows in X-rays that left it before our species existed. And still, it pulls. Quietly, steadily, across a distance that light takes 250 million years to cross. The gravity of that place reaches through the dark and bends the path of everything within its reach, including us, including the Milky Way, drifting at 600 kilometers per second toward a region we spent decades unable to see. The pull does not require our awareness of it. It was always there. And the Great Attractor does not stand alone. It is itself part of something larger, a broader architecture of mass and gravity that astronomers have been slowly tracing for decades, the way you might trace the outline of a continent by following the direction rivers flow. The region surrounding the Great Attractor belongs to a structure called the Hydra-Centaurus Supercluster, a vast congregation of galaxy clusters, groups and filaments spread across an enormous volume of space. The Great Attractor sits near its heart. The Norma Cluster, the hot intercluster gas, the thousands of galaxies bound together in that dense gravitational well. All of it is part of this larger whole, a whole that itself is part of something larger still. For a long time, astronomers drew the boundaries of our cosmic neighborhood in rough strokes. The Milky Way belonged to the local group. The local group belonged to the Virgo Supercluster. The Virgo Supercluster was our home in the large-scale structure of the universe. That was the picture for decades. Reasonable, workable, but incomplete. Then, in 2014, that picture changed. A team of astronomers led by Brent Tully and his colleagues did something quietly remarkable. They did not simply map where galaxies were. They mapped how galaxies were moving, the direction of their drift, the subtle lean of their trajectories through space. And from those flow lines, those gravitational currents, they drew a new boundary. A boundary defined not by position, but by motion. What they found was a supercluster far larger than anyone had previously recognized. They called it Laniakea. The name comes from Hawaiian. It means immeasurable heaven, and the name is fitting, not as poetry, but as description. Laniakea spans roughly 500 million light years. It contains the mass of about 100 million billion suns. 100 million billion. Each one a star. Each star a sun, quietly burning somewhere in the dark. Part of a galaxy, part of a cluster, part of a flow that bends, however gently, toward the same convergence point. The method that revealed Laniakea was, in its own way, as elegant as the structure itself. Tully and his colleagues reasoned that a supercluster could be defined the way a watershed is defined on Earth. When rain falls on a mountain range, the water flows downhill. Some of it flows east, some west, depending on which side of the ridge it lands. The ridge itself, the watershed divide, is the boundary between two drainage basins. Water on one side flows to one river. Water on the other side flows to another. Galaxies, it turns out, behave something like water. They flow along gravitational gradients. They drift toward regions of higher mass. And just as a watershed divide separates two drainage basins, a gravitational divide separates two superclusters. Galaxies on one side of the divide flow inward toward one convergence point. Galaxies on the other side flow toward another. Laniakea is one such basin. Every galaxy within it, tens of thousands of them, flows inward along gravitational streams toward the same convergence point. That convergence point, the gravitational low of the entire basin, corresponds to the Great Attractor region, the place we have been circling around in this conversation, the place the Milky Way has been drifting toward for as long as it has existed. The Great Attractor is not merely a local anomaly, then. It is the basin floor of our supercluster, the place toward which the rivers of galaxies run. And the Milky Way sits near the outer edge of Laniakea, far from the center, far from the attractor, on the quiet periphery of this immeasurable structure. We are not at the heart of things. We are somewhere near the rim, drifting inward along a gravitational current so gradual that no human lifetime, no civilization, no geological era could perceive it as motion. 600 kilometers per second sounds fast, and in human terms, it is beyond imagining. But against the scale of Laniakea, 500 million light years across, it is the slowest of drifts, a leaf turning on a still pond. The motion is real, measurable, confirmed by the faint asymmetry it leaves in the cosmic microwave background. But it is not urgent. It is not dramatic. It is simply the quiet consequence of existing inside a universe that has mass, and mass that has gravity, and gravity that has been accumulating and pulling for nearly 14 billion years. What makes Laniakea remarkable is not just its size. It is that it was invisible to us for so long, not because the galaxies were hidden, though many were, behind the zone of avoidance, but because we were looking at the wrong thing. We were mapping positions. We were cataloging locations. And from locations alone, the boundary of Laniakea is not obvious. Galaxy clusters blur into one another. Superclusters bleed at their edges. There is no wall, no gap, no clear line in the sky that says, here, the supercluster ends. But velocity tells a different story. Velocity carries the memory of force. A galaxy moving in a particular direction is moving that way because something pulled it, or is pulling it still. The direction of motion is a record of the gravitational landscape, not just where mass is now, but where it has been exerting its influence across billions of years. When Tully and his colleagues mapped those velocities, the structure of Laniakea emerged from the data the way a face emerges from a fog, gradually, then all at once. There is something worth sitting with in that. The idea that the shape of our cosmic home was written not in the positions of galaxies, but in the direction they were leaning. That the structure was always there, encoded in motion, waiting for someone to ask the right question. Not where are the galaxies, but where are they going? Laniakea contains the Virgo cluster, which anchors the older, smaller picture of our neighborhood. It contains the Great Attractor region, the Norma Cluster, the Hydra Centaurus Supercluster. It contains the Milky Way and the local group and the Andromeda Galaxy, which is itself drifting toward us on its own slow collision course, a separate story, a separate time scale, but part of the same vast gravitational choreography. 100 million billion solar masses, all flowing, all leaning, however imperceptibly, toward the same basin floor. The Great Attractor is not pulling us alone. It is pulling everything within Laniakea. Every galaxy in this immeasurable heaven is part of the same slow inward drift, the same gravitational conversation that has been unfolding since the first structures formed in the early universe. And yet the name feels right for another reason too. Immeasurable heaven. Not because we cannot assign numbers to it. We can, and we have. But because the numbers themselves resist being held in the mind. 500 million light years, 100 million billion suns, a convergence basin containing tens of thousands of galaxies, all flowing toward a point that is itself being pulled towards something even larger, further away, in a chain of gravitational influence that extends outward in every direction. The universe does not have a center we can point to, but it has structure, it has flow. It has basins and ridges and currents that move mass across distances so vast that the light crossing them carries the age of the universe in its travel time. And somewhere within all of that, near the quiet outer edge of one supercluster, in one arm of one spiral galaxy, something is resting, breathing slowly, drifting at 600 kilometers per second toward an immeasurable heaven without knowing it, without feeling it, without needing to. And every galaxy within Laniakea is doing the same thing. Not just the Milky Way, not just our nearest neighbors. Every galaxy within this vast supercluster, tens of thousands of them, scattered across 500 million light years, is moving along its own quiet thread of gravitational current, flowing inward toward the same place. The same convergence basin. Think of it like this. On Earth, water falling anywhere within a watershed will eventually find its way to the same river, the same valley floor. It does not matter where the rain lands. It does not matter how far the water travels or how many ridges and slopes it crosses along the way. The shape of the land determines where everything goes. Gravity does the rest. The scientists who mapped Laniakea borrowed that idea directly from hydrology. They looked not at where galaxies are, but at how they are moving, tracing the flow lines of peculiar velocity across the sky, the way a hydrologist might trace the drainage patterns of a continent. And what they found was a basin, a single, enormous gravitational low point toward which all the flows within Laniakea converge. That low point, the place where all those currents are headed, corresponds to the Great Attractor region. It is not a destination in the way a city is a destination. There is no surface to arrive at, no boundary you would cross and know you had arrived. It is more like the deepest part of a valley that has no floor you can stand on, just a region where the pull is strongest, where the mass is most concentrated, where the flows from every direction are drawn together and held. And the Milky Way is part of that flow. We sit near the outer edge of Laniakea, far from the center, far from the convergence. If you were to draw the supercluster as a map, all its filaments and tendrils and galaxy streams, our galaxy would appear somewhere near the periphery, like a small town near the border of a vast watershed. Far upstream from the valley it is slowly draining toward. The distance between us and the Great Attractor is roughly 250 million light-years. That is not a distance that yields easily to imagination. Light, traveling at the only speed the universe permits, would take 250 million years to cross it. When the light now leaving the Norma Cluster finally reaches us, it will carry an image of something that existed when the first dinosaurs were only beginning to appear on Earth. The universe we observe is always, in this sense, a record of the past. And yet, the pull is real. The motion is real. Right now, without any sensation of it, the Milky Way is being drawn along that gravitational current at roughly 600 kilometers per second. Not because something is pushing us, not because we are falling in any direction we could point to and feel, but because the shape of the universe around us, the distribution of mass across hundreds of millions of light years, creates a slope, and we are on it. All of this might suggest that the Milky Way is headed somewhere, that given enough time, we would close that distance, cross those 250 million light years, and arrive at the convergence basin at the heart of Laniakea. But that is not what will happen. The Milky Way will never reach the Great Attractor. Not because the pull is too weak, not because something will deflect us, but because the universe itself is expanding, and that expansion is accelerating. Space between distant objects is not just growing, it is growing faster over time. And at the distances involved, that expansion is not a gentle background process that gravity can simply overcome. It is a tide moving in the opposite direction, and it is winning. The Great Attractor pulls. The expansion of the universe pushes back, and at the scale of hundreds of millions of light years, the expansion does not lose. So the Milky Way drifts. It moves along its gravitational current, drawn toward a convergence it will never reach. Like a river that flows toward a coast, it cannot quite arrive at because the coast itself is slowly receding. The motion is real. The destination is not. There is something quietly profound in that. We are part of a flow that spans a supercluster. We are embedded in a structure so large that the light crossing it carries hundreds of millions of years of travel time. We are being pulled by a concentration of mass so enormous that it shapes the motion of tens of thousands of galaxies, and none of it will ever resolve into arrival. None of it will ever complete. The drift simply continues. Quiet, vast, without urgency and without end. It is worth resting with that for a moment. The universe is not moving toward a conclusion. It is not building towards something. The flows within Laniakea are not a journey with a destination. They are a condition, a state of being. The way a river is not trying to reach the sea, but simply expresses the shape of the land it moves through. And we are part of that expression. Every atom in the body resting here, every slow breath, every quiet heartbeat is part of a galaxy that is part of a supercluster, that is part of a gravitational flow that has been unfolding for billions of years. The watershed was shaped in the early universe, when the first structures began to condense out of an almost perfectly smooth sea of matter and energy. The currents have been running ever since. They will keep running long after any individual star has burned out, long after any particular galaxy has merged with its neighbors and grown quiet. The Great Attractor does not know we are here. It does not pull at us with any intention. It simply has mass, and mass curves the space around it, and curved space guides the motion of everything within it. That is all. That is enough. And somewhere in the middle of all of this, near the outer edge of an immeasurable heaven, far upstream from the convergence basin, drifting along a gravitational current that will never quite deliver us to its source, a small planet turns slowly in the dark. On that planet, something is breathing. Not moving toward anything tonight, not needing to, just resting within the flow the way everything in the universe rests within the flow, carried gently, without effort, without awareness, along currents laid down before the earth existed. The watershed holds you. The current is slow, and the distance is vast, and there is nowhere you need to arrive. Just this breath, and the quiet, and the drift. And yet, the drift has a limit. Not every current runs forever. Not every pole, however vast, can reach across all of space. There is something happening to the universe that works quietly against the Great Attractor. Something that has no center, no source, no name that fully captures it. It is simply the expansion of space itself, and it is not slowing down. It is speeding up. This is one of the stranger things cosmology has uncovered in the last few decades. The universe is not just growing. It is growing faster than it was yesterday and slower than it will be tomorrow. Something, called dark energy for lack of a better name, is woven into the fabric of space, and it pushes outward in every direction, at every point, all at once. And at sufficient distances, that push becomes stronger than any gravitational pull. Think of it this way. Gravity is a local thing. In cosmic terms, it reaches across millions of light years, even hundreds of millions. But space itself is expanding across billions. And the farther away a galaxy is, the more expanding space lies between us and it. More space means more expansion. More expansion means faster recession. There is a distance, a kind of horizon, beyond which galaxies are already moving away from us faster than light can travel through the space between us. Not because they are moving through space at that speed, but because space itself is stretching so quickly that the gap widens faster than anything can cross it. Those galaxies are, in a meaningful sense, already gone. We will never see them as they are now. We can only see them as they were, when the light they emitted was still close enough to reach us. And with every passing year, a few more galaxies cross that horizon. A few more slip beyond the reach of any signal, any force, any future contact. The Great Attractor cannot stop this. Its gravity is immense by any human measure. 10,000 trillion times the mass of our Sun, gathered across hundreds of millions of light years, bending the paths of thousands of galaxies. And still, the galaxies far enough away simply recede. The expansion wins. The current dissolves into the widening dark. The Milky Way itself will never arrive at the Great Attractor, not because the journey is too long, though it is, but because the universe will not hold still long enough. The attractor pulls, and we drift toward it, and the expansion stretches the space between us. And the net result is a motion that continues without ever completing. A river that flows toward a sea it will never reach. And here is the quieter part of this. The Great Attractor is not the end of the story. It is not even the largest gravitational presence shaping our motion, because the Great Attractor itself is being pulled. Deeper into the structure of things, roughly 650 million light years from where we are, there is a concentration of mass so large that astronomers have spent decades trying to fully measure it. It is called the Shapley Supercluster. The Shapley Supercluster is one of the most massive structures in the observable universe. It is not a single cluster, but a vast complex. Dozens of galaxy clusters gathered together, bound loosely by their mutual gravity, forming a kind of mountain range in the landscape of cosmic mass. Its gravitational influence reaches across hundreds of millions of light years in every direction, including toward us. The Great Attractor, that enormous convergence basin at the heart of Laniakea, is itself flowing toward Shapley. The watershed drains into a deeper watershed. The river feeds a larger river, and we, far upstream, Feel the pull of both, the nearer one more strongly, the distant one more subtly, but both present in the motion of our galaxy through space. Some cosmologists have come to think of the Great Attractor less as a destination and more as a waypoint, a place where gravitational currents gather before continuing onward, drawn by something larger still. The flow does not stop at the Norma Cluster. It continues, slower and more diffuse, in the direction of Shapley. How much of our motion comes from the Great Attractor, and how much from Shapley is still being worked out? The measurements are difficult. Shapley lies far enough away that the expansion of the universe complicates the picture. Separating the gravitational pull from the background expansion requires careful modeling, and the models depend on assumptions about dark matter, dark energy, and the large-scale structure of the cosmos that are still being refined. As far as we can tell, Shapley may contribute as much to our peculiar velocity as the Great Attractor itself, perhaps more. The two influences are entangled in the data, and disentangling them is slow, patient work. This is the nature of cosmology at these scales. The universe does not offer clean answers. It offers signals, faint and overlapping, arriving from hundreds of millions of light years away, carrying information about structures so large they barely fit inside the observable universe. And astronomers sit with those signals and build models and revise them and sit with them again. There is something restful in that image if you let it settle. Somewhere in an observatory or at a desk, someone is quietly looking at the motion of galaxies, not rushing, not forcing the data to say more than it can, just watching the slow drift of things and trying to understand where the currents lead. The Shapley Supercluster was named for Harlow Shapley, an astronomer who spent much of his life mapping the structure of the Milky Way and arguing, correctly, that our solar system was not at the center of it. He did not know about the supercluster that would carry his name. He could not have. The instruments did not exist. The concepts were not yet formed. And yet, the structure was there, all along, pulling, quietly, without intention, without awareness, simply by having mass. 650 million light years. The light we receive from the Shapley Supercluster left its source when the Earth was young by geological standards, but ancient by any human one. Before the first fish crawled onto land, before the first forests grew and fell and became the coal seams we would one day burn, that light has been traveling ever since, crossing the expanding dark, passing through the zone of avoidance, arriving finally at our instruments as a faint signal in a sea of signals. And from that signal, we infer a pull that has been shaping our motion for billions of years without our knowledge, a pull that will continue shaping it long after the last human thought has faded. The Shapley Supercluster does not know we have named it. It does not know we have measured it, or wondered about it, or lain awake at night trying to hold its scale in mind. It simply is. Mass, gathered over billions of years, curving the space around it, guiding the motion of everything within reach. And we are within reach, not close, not arriving, but within the long, slow gravitational conversation that connects our small corner of the cosmos to structures almost too large to speak of. The drift continues. Outward from the sun, outward from the galaxy's center, outward from the edge of Laniakea, drawn gently toward the Great Attractor, which is itself drawn gently toward Shapley, which may be drawn towards something else still, something not yet fully mapped, not yet fully named. Currents within currents. All of it moving, all of it quiet, all of it indifferent to the small warm creature lying still in the dark, breathing slowly, letting the weight of the body settle into the surface beneath it. The universe carries you without asking. and you are already, without effort, exactly where you are supposed to be. There is a word for the way galaxies move when they deviate from the smooth, even expansion of the universe. Peculiar velocity. It is a quiet, technical phrase, but it carries something almost philosophical inside it. Every galaxy in the universe is being carried outward by the expansion of space itself, that broad, even tide that has been flowing since the beginning. But layered on top of that tide, there are smaller currents, tugs and drifts caused by the uneven distribution of mass, galaxies leaning toward one another across the dark, clusters drawing in their neighbors, superclusters bending the flow of everything within their reach. These deviations from the smooth expansion, these leanings and driftings, are peculiar velocities. And they are, in their quiet way, one of the most powerful tools astronomers have ever found. Because a peculiar velocity is a kind of confession. When a galaxy moves faster than the expansion alone would carry it, or slower, or at an angle, that motion reveals something about the mass nearby, even mass that cannot be seen directly, even mass hidden behind dust, or too dark to emit light, or simply too far away to resolve clearly. The motion itself becomes the evidence. The drift becomes the map. This is how the Great Attractor was first suspected, long before anyone could see what lay behind the obscuring dust of our own galaxy's plane. Astronomers noticed that galaxies across a wide region of sky were not moving the way the smooth Hubble expansion predicted. They were leaning, flowing, converging on something, and the something, whatever it was, had to be enormous. Not a single object, not a single cluster, but a broad concentration of mass spanning hundreds of millions of light years, pulling everything in its vicinity along gravitational streams too gentle to feel, but too persistent to resist. The peculiar velocities told the story before the story could be read directly. And to read peculiar velocities at all, astronomers needed a reference frame, something to measure against, something that could stand in for the universe at rest. That reference frame exists. It is the oldest light in the universe, the cosmic microwave background, a faint, nearly uniform glow that fills all of space, the remnant warmth of an era nearly 14 billion years ago, when the universe was young and dense and hot. It cooled as space expanded. It stretched, and now it surrounds us from every direction, a soft hum of ancient radiation, almost perfectly smooth. Almost. Because when astronomers measure the cosmic microwave background carefully, they find a subtle asymmetry. One side of the sky appears very slightly warmer. The opposite side appears very slightly cooler. The difference is small, a fraction of a degree, but it is real, and it is consistent, and it has a name. The CMB dipole. It arises because we are moving. The Milky Way, the local group, the entire Laniakea Supercluster, all of it drifting through space at roughly 600 kilometers per second relative to the background radiation, moving toward the warmer side, moving, as far as we can tell, in the general direction of the Great Attractor. The light itself carries the record of our motion. There is something worth sitting with in that. The oldest light in the universe, imprinted in the first moments after the Big Bang, carries within it the faint signature of where we are going. Not because it was designed to, not because anything arranged it that way, simply because motion has consequences, and light is honest, and the universe keeps its own records without being asked. The dipole was one of the earliest clues that our galaxy was not at rest, that the smooth expansion of the universe was not the whole story, that something, somewhere, was pulling. But here is where the story becomes more layered, more uncertain, more interesting in the way that quiet things often are when you look at them long enough. Some cosmologists have come to think of the Great Attractor not as a destination, but as a waypoint, a place the flow passes through on its way to something larger. Because the Great Attractor is itself moving. The Norma Cluster, the Hydra Centaurus Supercluster, the entire Laniakea Basin, all of it drifting, not inward towards some fixed center, but onward, in the direction of the Shapley Supercluster, that vast concentration of mass lying some 650 million light-years away. And the peculiar velocities of galaxies across our region of space, when mapped carefully, suggest that Shapley's gravitational influence reaches all the way to us. That our motion is not simply toward the Great Attractor, but through it, towards something beyond. Currents within currents. The Great Attractor, in this view, is less a final answer than a chapter in a longer sentence. A gravitational waypoint in a flow that extends further than we can easily trace. The Milky Way is drawn toward it, yes, but the Great Attractor is drawn toward Shapley, and Shapley may be drawn toward structures not yet fully resolved, not yet fully named, lying at the edges of what current surveys can reach. The peculiar velocity field, when mapped across hundreds of millions of light-years, does not show a simple picture. It shows something more like a landscape. Ridges and valleys of gravitational influence, flows converging and diverging, attractors nested within attractors, the whole structure shaped by the uneven distribution of matter that has been accumulating since the first tiny fluctuations in the early universe began to grow. And all of this vast, slow, gravitational choreography is encoded in the motions of galaxies, in the small deviations from the smooth expansion, in the peculiar velocities that whisper, if you know how to listen, about the shape of everything. The cosmic microwave background holds the baseline. The galaxy motions hold the deviations. And from the difference between them, astronomers reconstruct a picture of the universe's hidden architecture, the dark matter scaffolding, the filaments, the voids, the nodes where mass has gathered over billions of years into structures almost too large to name. It is slow work, patient work. The kind of work that requires measuring the positions and velocities of thousands of galaxies, correcting for every known source of error, and then sitting with the uncertainty that remains. The parts of the sky still obscured, the structures still beyond the reach of current instruments, the questions that will take another generation of telescopes to answer. But the picture that has emerged, even now, even incomplete, is one of extraordinary coherence. The universe is not random at large scales. It has structure, it has flow, it has something that functions in a loose and impersonal way, like direction, not purpose, not intention, but the quiet inevitability of mass attracting mass, of gravity doing what gravity has always done, patiently, across distances and timescales that have no human equivalent. And somewhere in all of that, somewhere in the vast, slow drift of 100 billion galaxies moving along their gravitational streams, there's a small spiral galaxy, unremarkable in most respects, carrying within it a small warm planet, carrying within it a small warm creature lying still in the dark, moving at 600 kilometers per second toward a region of excess mass it will never reach, measured against the oldest light in the universe, part of a flow that extends further than any current map can follow, and unaware, in this moment, of any of it. The breath slows. The body settles. The drift continues, as it always has, as it always will. Quiet, vast, and patient beyond any measure of patience the waking mind can hold. And yet the story does not end with the drift. There is something else beneath it. something that took a long time to see, not because it was subtle, but because it was everywhere, and everywhere is the hardest place to look. Long before astronomers had a name for the Great Attractor, before they had mapped the flow of galaxies or traced the boundaries of Laniakea, there was a quieter clue, a whisper in the oldest light in the universe. The cosmic microwave background, that faint, ancient glow left over from the early universe, roughly 380,000 years after the Big Bang, fills the sky in every direction. It is almost perfectly uniform. Almost. When astronomers measured it carefully, they found a slight asymmetry. One side of the sky appeared very slightly warmer, the other very slightly cooler. Not by much. The difference is a fraction of a degree, smaller than almost anything else in cosmology. But it was there, and it was real, and it meant something. It meant we were moving. The pattern is called the CMB dipole, and it arises the same way the pitch of a passing sound shifts depending on whether the source is moving toward you or away. Light from the direction we are moving toward gets compressed, ever so slightly, into shorter wavelengths, slightly warmer. Light from behind us stretches slightly cooler. The dipole told astronomers, decades before the full picture emerged, that our galaxy was not sitting still relative to the universe. It was moving, and moving with purpose, not random, not chaotic, but directed, flowing towards something. That something, we now understand, is the Great Attractor region. The dipole was one of the earliest fingerprints of a gravitational influence so large it had not yet been named. And yet, even knowing the direction, even measuring the speed, the question remained, what, exactly, is doing the pulling? The visible galaxies in the Norma Cluster, the thousands of bright points of light bound together in that dense region of space, are not enough. The stars, the gas, the dust, everything that glows, everything that can be seen or photographed or cataloged, accounts for only a fraction of the mass needed to explain the motion. The rest is something else. Something that does not emit light, does not reflect it, does not interact with it in any way that our instruments can directly detect. And yet it is there, because gravity does not lie, and the gravity in the Great Attractor region is far stronger than the visible matter alone could produce. This is dark matter. Roughly 85% of all the matter in the universe is dark matter. Not 15%. Not a small correction. 85%. The stars, the planets, the gas clouds, the galaxies themselves, everything that has ever been seen or touched or measured makes up only about 15% of the matter that exists. The rest is invisible. It passes through ordinary matter without interaction. It does not clump into stars or planets. It does not cool and collapse the way ordinary gas does. It simply exists, distributed through space in vast, diffuse halos and filaments, felt only through the curvature it creates in the fabric of space-time around it. We have never directly detected a single dark matter particle. Every attempt, in deep underground laboratories shielded from cosmic rays, and detectors cooled to fractions of a degree above absolute zero, has so far returned silence. And yet the evidence for its existence, gathered from galaxy rotation curves and gravitational lensing and the large-scale structure of the universe, is overwhelming. It is one of the most certain things in cosmology, and one of the least understood. What we do know is what it does. Dark matter forms the scaffolding, the invisible architecture upon which everything visible is arranged. Long before the first stars ignited, dark matter was already gathering, pulled together by its own gravity, forming halos and filaments and nodes across the young universe. And ordinary matter, the kind that makes stars and planets and everything alive, fell into those structures, settled into them. Like water finding the contours of a landscape it did not shape. The galaxies we see are not randomly scattered. They trace the dark matter beneath them, the way foam on the surface of water traces the currents below. And those currents have a shape. The shape is called the cosmic web. Across hundreds of millions of light years, dark matter and the galaxies embedded within it are arranged into long, thin structures, filaments, that stretch between dense nodes of mass and curve around vast, near-empty regions called voids. The filaments are not sharp lines. They are broad, diffuse threads, each one containing the mass of countless galaxies, each one connecting one cluster to another across distances that take light hundreds of millions of years to cross. The Great Attractor sits at one of these nodes, a place where several filaments converge, where mass has been accumulating for billions of years, drawing in galaxies from the surrounding web along the gravitational streams that run through the filaments like rivers running toward the sea. The Milky Way is on one of those streams. It is not falling freely through empty space toward a single point. It is moving along a filament, carried by the slow, patient pull of a structure far larger than any single cluster, embedded in a web of dark matter that extends in every direction further than current maps can fully trace. When astronomers first began to understand this, when the full picture of the cosmic web began to emerge from surveys and simulations, there was a quiet recognition that the universe at large scales is not chaotic. It is structured, deeply, intricately structured, not by any intention, but by the simple, relentless logic of gravity acting on matter over billions of years. Tiny fluctuations in the density of the early universe, quantum variations, smaller than anything that can be directly perceived, grew over time into the filaments and voids and nodes we see today. The cosmic web is the grown form of those ancient seeds, and the Great Attractor is one of the places where that growth has been most pronounced, where mass has gathered most deeply, where the gravitational well runs most steeply. It is, in a sense, one of the universe's oldest and most patient accumulations. And the dark matter within it, invisible, silent, undetectable by any light, is the majority of what makes it what it is. There is something quietly humbling in that. The thing pulling our galaxy across hundreds of millions of light years, the thing that left its signature in the oldest light in the sky, the thing that shaped the web along which all of this motion flows, most of it cannot be seen. Most of it is made of something we do not yet understand. The universe keeps more than it reveals. And perhaps that is fitting, that the largest structures, the deepest currents, the forces shaping the motion of 100 billion galaxies, perhaps it is fitting that most of this happens in a kind of darkness. Not the darkness of absence, but the darkness of something present and vast and simply beyond the reach of light. The filaments stretch on, the nodes accumulate, the streams flow inward along paths laid down before the Earth existed. And somewhere along one of those streams, a small spiral galaxy drifts, carried not by any force it chose, not toward any destination it will reach, but along the quiet, inevitable contours of a universe that was always, from the very beginning, shaping itself this way. The breath slows. The body is still. The dark matter is there, as it has always been, surrounding, threading through, holding the shape of everything. Unseen and patient and vast beyond any resting mind's need to follow. And at the center of all of that, at the place where the streams converge and the filaments meet, there sits the Great Attractor region. Not at the end of a single thread, but at a crossing, a junction where several of those vast dark filaments come together, the way rivers meet at a delta, the way roads converge at the heart of an old city. Except the scale here is not a city, not a continent, not even a solar system. The filaments meeting at this region stretch across hundreds of millions of light years in every direction, and the Great Attractor sits quietly at their intersection, accumulating, holding, drawing inward everything that flows along those threads. It is, in a sense, a knot in the fabric, a place where the web pulled tighter. And between those threads, between the filaments, between the nodes, between every bright concentration of matter, there is something else entirely. There is emptiness. Not the ordinary emptiness of space between stars, which is already difficult to hold in the mind, but something far larger, the cosmic voids. Voids are the spaces between the filaments of the cosmic web. They are regions where matter is sparse almost beyond imagining, where galaxies are rare, where the threads of dark matter thin out to nearly nothing, where the universe has, over billions of years, drained itself away toward the surrounding walls and filaments. And these voids are not small. They occupy most of the volume of the universe. If you were to take all of space, everything the observable universe contains, and ask where most of that volume actually resides, the answer would not be in the clusters, not in the filaments, not in the bright nodes where galaxies gather. Most of the volume of the universe is void. Vast, quiet, near empty space, stretching in every direction between the luminous threads. The filaments are where the matter is. The voids are where the universe simply opens. And we are not outside of one of those voids. Looking in, we may be inside one. The void nearest to our region of space is called the KBC void. It is one of the largest known underdensities in the observable universe, and its scale is difficult to hold steady in the mind. It may span over 1 billion light years across, a region of space so large that the entire Laniakea Supercluster, 500 million light years wide, containing the mass of 100 million billion suns, fits within it, with room to spare. The Milky Way, drifting along its quiet path, sits inside this vast underdensity, surrounded not by the dense walls of a filament, but by the relative emptiness of a cosmic hollow. And this matters. It matters in a way that is still being worked out, still being debated carefully among researchers who study the large-scale structure of the universe. Because if we are inside a void, a region where the average density of matter is lower than the cosmic mean, then the gravitational pull we feel from the denser regions surrounding us would be amplified. Not because the Great Attractor is more massive than it appears, but because the emptiness behind us, the underdensity in which we sit, reduces the pull from that direction, leaving the pull from the Great Attractor region less balanced, more pronounced. Some researchers have proposed exactly this, that our location inside the KBC void may be part of why the Great Attractor's influence registers so strongly in the motions of our galaxy and our neighbors. That we are not simply being drawn toward a concentration of mass, but also, in a sense, sitting in a hollow that tilts the balance. The void pushes, in its quiet way, by simply being empty. And the attractor pulls by being full. Between the two, the Milky Way drifts. It is a strange thought to rest with, that the emptiness around us is not neutral, that the absence of matter in one direction shapes our motion just as surely as the presence of matter in another. The universe moves us not only by what it contains, but by what it lacks. And all of this, the filaments, the nodes, the voids, the attractor, the hollow in which we drift, all of it traces back to something almost impossibly small. In the very first moments after the Big Bang, the universe was not perfectly smooth. It was nearly smooth, nearly uniform, but not quite. There were tiny variations in density, fluctuations so small they existed at the quantum scale, smaller than any atom, smaller than any particle we can directly observe. Ripples in the fabric of the earliest universe, laid down in the first fraction of a second of existence. Those fluctuations were not random noise to be smoothed away. They were the seeds. Over hundreds of millions of years, then billions of years, gravity worked on those seeds. The regions that were very slightly denser than average drew in more matter. The regions that were very slightly less dense gave matter away. Slowly, the small differences grew. The denser regions became filaments. The less dense regions became voids. The densest intersections became the great nodes, the clusters, the attractor regions. What we see now, the entire vast architecture of the cosmic web, is the grown form of those ancient, quantum-scale whispers. The Great Attractor is not an accident. It is not an anomaly. It is the natural outcome of a universe that began with the faintest possible unevenness and then spent 14 billion years letting gravity do its patient work. Every filament was written in those first moments. Every void was written there too. The hollow in which the Milky Way drifts, the crossing where the Great Attractor gathers its mass, the streams along which 100,000 galaxies flow, all of it was, in some sense, already present in the structure of the universe before a single star had formed. Before the Earth existed, before the Sun existed, before any of the matter that makes up this moment had taken any recognizable shape at all. The quantum fluctuations became the cosmic web, and the cosmic web became the context for everything that followed. It is a long chain of consequence, longer than any chain we encounter in ordinary life, and yet it is unbroken. The fluctuation became the filament became the flow became the drift of a galaxy. The drift of a galaxy became the motion of a solar system. The motion of a solar system became, in some infinitely small way, part of the stillness of this moment. Your body at rest, the breath moving slowly, the mind releasing its hold on the day. All of it carried, without effort, without awareness, along a path that was shaped before the first stars burned. The voids open around us in every direction, vast and quiet. The filaments stretch away into distances that have no human measure. The Great Attractor waits at its crossing, patient as gravity itself, drawing the streams inward along lines that were laid down at the beginning of everything. And the universe continues its slow, enormous work, indifferent to the scale of any single life, indifferent to the passage of any single night. The drift continues. The web holds its shape, and somewhere within it, very small, very still, a mind lets go of the last thread of waking thought and rests. The structures you have been drifting through tonight, the filaments, the voids, the slow gravitational rivers flowing toward the Great Attractor, none of them appeared suddenly. They grew. The way a crystal grows from a single impurity in cooling water, the way frost traces its branching lines across a cold pane of glass, slowly, following rules laid down long before the first pattern became visible. It began in the first fraction of a second after the Big Bang. Not minutes, not hours. A fraction of a second, a sliver of time so thin it has no name in ordinary experience. In that moment, the universe was not yet the universe we know. It was a place of almost perfect uniformity, Almost, but not quite. Threaded through that early heat and density were tiny variations, regions where the energy was, by the smallest imaginable margin, slightly denser than the regions around them. These were quantum fluctuations, disturbances at the smallest possible scale of reality, the kind of trembling that matter and energy cannot entirely suppress, even in conditions of near-perfect stillness. They were not designed. They were not placed with intention. They were simply the irreducible texture of existence at its most fundamental level. And yet, everything you have heard tonight descended from them. Over hundreds of millions of years, then billions, those tiny overdensities pulled matter toward themselves. Gravity is patient. It does not hurry. It simply persists. And in persisting, it gathered hydrogen and helium into the first clouds, the first stars, the first galaxies. The denser regions grew denser still. The emptier regions grew emptier. The contrast deepened, slowly, the way a photograph develops in a darkroom, the image emerging, not all at once, but gradually, detail by detail, out of what looked at first like nothing. The filaments formed along the edges where overdense regions met. The voids opened in the spaces between. The nodes, the great crossing points where filaments intersected, accumulated mass the way rivers accumulate water at a delta. In the great attractor region, that broad, deep concentration of mass toward which the Milky Way has been drifting for as long as it has existed, was one of those nodes, not an accident, not an anomaly, a natural outcome. This is something worth resting with for a moment. The great attractor is not strange. It is not an exception to the rules of the universe. It is what the rules of the universe, followed patiently over billions of years, inevitably produce. Astronomers have confirmed this not only by observation, but by calculation, by building, inside powerful computers, models of the entire universe, or at least of a representative piece of it, and watching what happens when the same rules are applied from the beginning. The most well-known of these efforts is called the Millennium Simulation. It was run in the early years of this century, using the known laws of gravity, the known proportions of dark matter and ordinary matter, and the known initial conditions of the early universe, and it was allowed to run forward through simulated time. What emerged, after billions of simulated years, was a cosmic web, filaments of dark matter and galaxies stretching across the virtual sky, voids opening between them, and at the intersections of the filaments, dense concentrations of mass, nodes that looked, in their scale and character, very much like the great attractor region we observe in the real universe. The simulation did not know about the great attractor. It was not told to produce one. It simply followed the physics. And the physics produced it anyway. There is something quietly reassuring in this. The universe is not arbitrary. Its largest structures are not random accidents scattered without pattern across an indifferent void. They are the legible result of simple rules, applied with perfect consistency across unimaginable spans of time. The great attractor was always going to be there, something very much like it, in some direction, at some distance. It was written into the initial conditions of the universe before the first atom had formed. At the nodes of the cosmic web, the work of accumulation continues even now. Galaxy clusters grow not by creating new matter, but by drawing in what already exists nearby. Smaller groups of galaxies, moving along the filaments, fall gradually toward the deeper gravitational wells at the nodes. Over billions of years, they are absorbed. Their galaxies become part of the cluster. Their dark matter halos merge with the larger halo. The cluster grows more massive, and in growing more massive, it draws more strongly on what surrounds it. This process is called accretion. and it is one of the most fundamental processes in the universe. Stars accrete gas. Black holes accrete stars. Galaxy clusters accrete smaller clusters and groups. The logic is the same at every scale. Mass draws mass. Gravity compounds. When two galaxy clusters merge, the event is not quiet. The clusters themselves are not solid objects. They are vast, diffuse structures, thousands of galaxies moving through clouds of superheated gas, all of it threaded with dark matter. When two such structures collide, the galaxies themselves rarely strike one another directly. The spaces between stars are too large for that. But the hot gas that fills the space between galaxies, the intracluster medium, does collide. And the collision releases energy on a scale that is difficult to hold in the mind. Shock waves move through the intracluster gas at millions of kilometers per hour. The gas is compressed and heated further, already at temperatures of tens of millions of degrees, pushed higher still by the violence of the merger. Enormous plumes and arcs of X-ray emitting gas are thrown outward into the surrounding intergalactic space. The energy released in a major cluster merger can exceed, by many orders of magnitude, the total energy output of every star in both clusters combined. And yet, from any ordinary human vantage point, it would appear to happen in slow motion. The timescales involved are hundreds of millions of years. What looks, in an X-ray image, like a frozen moment of catastrophe is in fact a process unfolding across a span of time longer than the age of the Earth. The universe conducts its most violent events at a pace that feels, from the inside, like stillness. Much like sleep, the body lying still, the breath slow and even. And beneath that apparent stillness, an enormous amount of quiet work being done. Cells repairing themselves, memories being sorted and stored, the nervous system releasing the tensions of the day, the brain moving through its own deep cycles, its own slow waves. Stillness is rarely the absence of process. It is often process at its most essential, stripped of urgency, freed from the noise of waking attention. The merging clusters pour their energy into the intergalactic medium, that thin, hot, nearly invisible gas that fills the spaces between galaxies. It is not nothing. That medium, it carries the record of every collision, every shock wave, every outflow from every galaxy that has ever passed through it. It is a kind of memory, written in heat and density rather than in words. And the great Attractor region, where so much of this merging and accreting has taken place over so many billions of years, holds within it a record of the universe's long history of accumulation. Every galaxy that fell inward along a filament, every smaller cluster absorbed into a larger one, every shock wave that moved through the intracluster gas and faded slowly into warmth. All of it is there, encoded in the structure of what exists now. The universe keeps its own record. Patient, complete, indifferent to whether anyone reads it. And the drift continues, as it always has, as it always will. For as long as the filaments hold their shape and the nodes hold their mass, and the slow rivers of galaxies keep moving, without hurry, toward the place where gravity has been quietly waiting since before the first stars burned. That gas between the galaxies is not cool, not quiet. It is extraordinarily hot. The intracluster medium, that thin but vast ocean of plasma filling the spaces between galaxies within a cluster, can reach temperatures of tens of millions of degrees. In some of the most massive clusters, the temperature climbs even higher, 100 million degrees, more than 6 times hotter than the core of our own sun. And yet, it glows not in visible light, but in X-rays, wavelengths so energetic that only space-based telescopes can detect them. When astronomers turn those instruments toward the Norma Cluster, toward the heart of the Great Attractor region, they see the gas shining, a diffuse, ghostly luminescence spread across millions of light years. It is the signature of matter under enormous gravitational pressure, heated not by any fire, but by the slow, relentless compression of gravity itself. This is what it means to fall into a cluster. A galaxy drifting inward along a filament, drawn by the accumulated mass of thousands of other galaxies, eventually crosses into that hot medium. And when it does, something begins to happen to it. Something gradual and irreversible. The galaxy carries its own gas, cool clouds of hydrogen and helium, the raw material from which new stars are born. That gas is loosely held, spread across the galaxy's disk in great sweeping arms. And as the galaxy moves through the intracluster medium, the surrounding plasma pushes back, not gently. The pressure of that hot gas against the galaxy's motion is enough, over time, to strip the cooler gas away, to peel it from the disk the way wind peels leaves from a branch. This process has a name, ram pressure stripping, and it leaves a visible mark. Galaxies caught in the act of falling into a cluster sometimes show long trailing streamers of gas, pulled back behind them like the tail of a comet. The gas that was once the seed of future stars is now dispersed into the intracluster medium, heated, mixed, lost. What remains is a galaxy slowly running out of the material it needs to make new stars. The star formation does not stop all at once. It fades. The youngest, brightest stars burn through their fuel and are not replaced. The blue light of hot young stars dims. What is left behind is the older population, the cooler, redder stars that burn slowly and last for billions of years. The galaxy grows quieter, its color shifting from the blue-white of active star formation toward the deep amber of an aging stellar population. Over time, over hundreds of millions of years, a spiral galaxy falling into a dense cluster can be transformed almost entirely. Its gas is gone. Its star formation has ceased. Its spiral arms, once defined by the density waves that triggered new star birth, gradually lose their structure. What remains is something rounder, smoother, more featureless. An elliptical galaxy. The Great Attractor region contains a higher than average proportion of these large elliptical galaxies, and that is not a coincidence. It is a record. Each one of those smooth, rounded forms carries within it the history of what it passed through. The stripping, the merging, the long, slow quenching of its star-forming life. Because ram pressure stripping is only part of the story. Elliptical galaxies are also thought to form through mergers, when two galaxies of comparable size fall toward each other and collide. The result is not a clean impact, but a long, chaotic gravitational dance. The spiral arms are disrupted, the gas is compressed and then dispersed. Stars that once moved in orderly circular orbits are scattered into new trajectories, crossing and recrossing the center of the merged system. Over hundreds of millions of years, the combined structure settles, and what it settles into is often an ellipse, a smooth, slowly rotating cloud of stars with no preferred plane, no spiral structure, no significant reservoir of cold gas. In dense cluster environments, this process is accelerated. Galaxies are closer together. They move faster relative to one another. The probability of a close encounter, a gravitational interaction, a merger, is higher than it would be in the quieter outskirts of the cosmic web. The Great Attractor region, where filaments converge and mass has been accumulating for billions of years, is exactly the kind of environment where mergers happen often, where the transformation from spiral to elliptical is not rare, but expected. And so, the population of galaxies near the core of that region reflects its history. Large ellipticals, some of them among the most massive galaxies in the observable universe, sitting at the centers of clusters, having grown through the absorption of smaller galaxies over cosmic time. They are the endpoint of a long process of accumulation. The same process, scaled down, that defines the Great Attractor itself. The oldest stars in some of these elliptical galaxies formed more than 10 billion years ago, before the solar system existed, before the Earth existed. They formed in the early universe, when gas was abundant and star formation was vigorous, and they have been burning quietly ever since. The galaxy around them has changed enormously, merged, stripped, reshaped. But those ancient stars persist, carrying within their chemical composition the record of the conditions that existed when the universe was young. There is something very still about an elliptical galaxy compared to a spiral, which is alive with structure and motion and the ongoing business of star formation. An elliptical is quieter. Its stars move in long, slow, crossing orbits. Its light is even and warm. It has, in a sense, already done most of what it will ever do. And yet, it is not finished. Even now, the largest ellipticals at the centers of clusters continue to grow. Small galaxies that wander too close are absorbed. Their stars are added to the outer envelope of the central giant. This process, called cannibalism, in the literature, though the word carries more drama than the reality deserves, is slow and gentle by cosmic standards, a gradual accumulation, one small galaxy at a time, over billions of years. The Great Attractor region is full of this kind of quiet, ongoing transformation. Mass flowing inward along filaments, galaxies falling into clusters, gas being stripped and heated and mixed into the intracluster medium, smaller galaxies merging into larger ones. The whole region is a place of convergence, and convergence, over time, produces these large, settled, ancient structures. It is easy to think of the Great Attractor as a destination, a place toward which things move. But it is also a place where things have already arrived, where the long journey along the filaments has ended for many galaxies, and what remains is the quiet aftermath of all that motion. The ellipticals sitting at the centers of clusters, the hot gas glowing in X-rays, the intracluster medium holding within it the chemical traces of every galaxy that was ever stripped or disrupted or consumed. The drift continues for those still on their way. But for the galaxies already deep within the Attractor region, the journey is largely over. They have settled into the gravitational well. They move, still, relative to one another, hundreds of kilometers per second, even now. But they are bound. They will not escape. They are part of the structure now, woven into it. Their futures tied to the slow evolution of the cluster itself. And the cluster will continue to grow, absorbing what comes to it. Patient as only gravity can be patient, indifferent to time in the way that only very large, very old things can afford to be. The stars inside those elliptical galaxies, the ones already settled, already bound, are among the oldest things we can point to in the sky. Some of them formed more than 10 billion years ago. 10 billion years. Before our sun existed, before the Earth had condensed from its cloud of dust and gas, before any of this, the oceans, the continents, the slow crawl of life across a young planet, those stars were already burning. They formed in the early universe, when gas was abundant and the conditions for star formation were rich. They burned through their fuel, evolved, and settled into the quiet remnants they are today. Old, cool, red. the embers of a fire that was lit before our solar system had any reason to exist. And yet, we can see them. Not because they are close, but because light, for all its patience, travels. It travels at roughly 300,000 kilometers every second, a speed so constant, so fundamental, that the universe appears to have written it into its own structure, not as a rule imposed from outside, but as something deeper, something that emerges from the nature of space and time themselves. Albert Einstein understood this in a way that still quietly reshapes how we think about everything. He showed that the speed of light is not simply the speed of a very fast thing. It is the speed at which causality itself propagates, the rate at which any event can influence any other event, the boundary between what can be connected and what cannot. Nothing with mass can reach it. The closer a massive object gets to the speed of light, the more energy it requires to accelerate further, and the more its mass, in a sense, resists. Time slows for it. Distances compress. The universe rearranges itself around the traveler in ways that protect the limit. Light itself, massless, traveling always at sea, does not experience this resistance. It does not experience time at all. As far as we can tell, a photon, in its own frame, travels from its source to its destination in no time whatsoever. It is emitted, and it arrives. The journey between those two moments, for the photon, does not exist. But for us, watching from the outside, the journey takes exactly as long as the distance requires. And so when we look at the Norma Cluster, the dense heart of the Great Attractor region, we are not seeing it as it is. We are seeing it as it was. Roughly 250 million years ago, light left the Norma Cluster and began its journey toward us. At that moment, on a small planet orbiting an unremarkable star in what would one day be called the Milky Way, dinosaurs were walking the Earth. The Triassic period was just beginning. The continents were still joined into a single landmass. The first mammals had not yet appeared. All of that has come and gone. Entire species rose and vanished. The continents drifted to where they are now. The dinosaurs lived for 160 million years and then disappeared. Mammals diversified, primates emerged, and eventually, after all of that, something looked up at the sky and began to wonder what it was seeing. And the light that left the Norma Cluster before any of that happened only now arrives. It carries information about a cluster that no longer exists in quite that form. The Norma Cluster has continued to move, to evolve, to accrete. In the 250 million years since that light departed, the cluster has followed its own gravitational path further along. Galaxies have fallen into it. Gas has been stripped and heated. The structure has deepened. What we see is a portrait of the past. This is always true in observational cosmology. Every telescope is a time machine, not by design, but by necessity. The further we look, the further back we see. The great attractor we observe, the one we have mapped, the one whose gravitational influence we have inferred, is the one that existed long ago. We are inferring the present from the past, always building a picture of now from light that left its source before now existed. It is a strange kind of knowledge, indirect, delayed, assembled from echoes. And yet it is the only kind available to us. The universe does not offer a faster channel. Light is the fastest messenger there is, and even light takes time. This is part of why the zone of avoidance has been such a persistent obstacle. The dust and gas of our own galaxy's plane do not merely block visible light, they scatter and absorb it, erasing the information carried by photons that have traveled for hundreds of millions of years. All that time in transit, and then lost in the final fraction of the journey, swallowed by the interstellar medium of our own home. Infrared and radio wavelengths pass through more easily, and astronomers have used them to peer behind the obscuring plane, finding galaxies that optical surveys could not reach. But the picture remains incomplete. That is beginning to change. The Square Kilometer Array, a radio telescope of extraordinary scale. Its antennas spread across 2 continents, will, when fully operational, map the zone of avoidance in detail that was not previously possible. It will detect radio emissions from hydrogen gas in galaxies hidden behind the plane of the Milky Way. Galaxies that have never been cataloged, never been named, never been included in our maps of the local universe. Some of them may be significant. Some may be part of structures that alter our understanding of the flows we have been tracing. The Great Attractor's true shape, the full extent of its mass, the precise geometry of its gravitational influence may look somewhat different once those hidden galaxies are accounted for. This is not a failure of what came before. It is simply how knowledge moves. Each generation of instruments reveals a layer that the previous generation could not reach, and each new layer asks new questions. The Rubin Observatory, surveying the southern sky with a camera of remarkable sensitivity, will trace galaxy flows across vast regions with a precision that current surveys cannot match. It will add millions of galaxies to the peculiar velocity maps, tightening the picture of how matter is distributed, how the flows converge, where the true centers of gravitational influence lie. And with better maps will come better questions. Whether the Shapley Supercluster is the dominant influence on our motion, whether some even more distant structure plays a role, whether the dipole repeller and the Great Attractor together account for the full pattern of our drift, these are questions that remain open, held gently in the uncertainty that honest science always carries. The answers will come slowly, as they always do, through careful observation, through instruments that take years to build and decades to operate, through the patient accumulation of data that no single lifetime is long enough to complete. There is something restful in that. The universe does not hurry. The light from the Norma Cluster took 250 million years to arrive. The structures we are mapping formed over billions of years. The questions we are asking will take generations to answer. And somewhere in all of that slowness, in the vast, unhurried scale of cosmic time, the urgency of any single moment becomes very quiet. The oldest stars in those elliptical galaxies have been burning for 10 billion years. They do not know they are being observed. They simply continue. And still, the work continues. Not with urgency, but with the quiet persistence that good science requires. One of the instruments that will carry that work forward is already taking shape in the mountains of northern Chile, the Vera C. Rubin Observatory. When it begins its full survey of the southern sky, will trace the motions of millions of galaxies with a precision that was not possible before. Its legacy survey of space and time, a decade-long program of observation, will build peculiar velocity maps of a depth and resolution that may finally settle some of the questions that have remained open for decades. Peculiar velocity maps. The phrase sounds technical, and it is, but the idea behind it is almost simple. Every galaxy in the universe is carried along by the expansion of space. That expansion is smooth, predictable, described by what cosmologists call the Hubble flow. But galaxies also have their own additional motions, small deviations from that smooth expansion caused by the gravitational pull of the mass around them. Those deviations are peculiar velocities, and by measuring them carefully across millions of galaxies, astronomers can reconstruct the underlying distribution of mass, even the mass that cannot be seen directly. It is a little like watching leaves on the surface of a river. The river carries everything downstream, But the leaves also drift sideways, eddy near rocks, slow near the banks. By watching how the leaves move relative to the current, you can infer the shape of the riverbed beneath. The galaxies are the leaves. The Hubble expansion is the current, and the Great Attractor, the Shapley Supercluster, the filaments and voids of the cosmic web. These are the hidden contours of the riverbed. The Rubin Observatory will give us a far more detailed picture of those contours than we have ever had. And one of the things that picture may clarify is the relative influence of the structures pulling and pushing on our motion. Because the story of the Great Attractor, it turns out, may not be only a story of attraction. In 2017, a team of astronomers mapped the full three-dimensional velocity field of galaxies in our cosmic neighborhood. They were not only looking for where galaxies were flowing toward, they were also looking for where galaxies were flowing away from. And what they found, in the direction roughly opposite to the Great Attractor, was a large underdense region, a void, from which galaxies appeared to be receding outward in all directions. They called it the dipole repeller. The name captures something important. A void does not push in the way a hand pushes. There is no force emanating from empty space. But a region with less mass than its surroundings exerts less gravitational pull. And so galaxies near a void are drawn away from it, toward the denser regions on the other side. The effect is indistinguishable, in its outcome, from a gentle push. The void repels not by acting, but by the absence of the pull that would otherwise hold things in place. And so our motion through the universe may be the result of two things working together: a pull from one direction, the Great Attractor, and beyond it, the Shapley Supercluster, drawing our galaxy and everything around it along gravitational streams toward a distant convergence, and a push from the other direction, the dipole repeller, a vast near emptiness whose lack of gravity allows the pull from the far side to go unanswered. The Milky Way, in this picture, is not simply falling towards something, it is also moving away from something. The drift is shaped by the entire surrounding structure, by presence and absence both, by mass and the lack of it, by the full three-dimensional landscape of the cosmic web in which we are embedded. There is something quietly profound in that. We tend to think of motion as caused by forces acting on us. Something pulls, and we move toward it. But the universe is more subtle than that. Our trajectory through space is the sum of every gravitational influence in every direction, near and far, seen and unseen. The Great Attractor is part of that sum. The dipole repeller is part of that sum. The Shapley Supercluster, 2.5 times further away, is part of that sum. And there may be structures beyond Shapley, not yet fully mapped, that contribute their own quiet weight to the calculation. The Rubin Observatory's maps will help untangle these contributions. By tracing galaxy flows across the southern sky with new precision, it will become clearer which structures dominate our motion and which are secondary. Whether the Shapley Supercluster is the true gravitational anchor of our drift, or whether some even more distant concentration of mass plays a larger role than current models suggest. These are questions the next generation of surveys is designed to answer. And the answers, when they come, will not arrive as sudden revelations. They will accumulate slowly, the way all cosmological knowledge accumulates. A survey that runs for 10 years data, that takes years more to process and interpret papers that are debated, refined, revised. Understanding that deepens gradually, like light returning to a room as the sun rises. That slowness is not a limitation. It is the nature of the questions being asked. The structures we are trying to understand formed over billions of years. The light we use to observe them has been traveling for hundreds of millions of years. The instruments we build to detect that light take decades to design and construct, and the human minds that interpret the data are themselves the product of 4 billion years of biological history. Briefly awake, briefly curious, briefly able to ask where they are and how they came to be moving in this particular direction at this particular speed. There is a kind of proportion in that. The scale of the question matches the scale of the effort required to answer it. And for now, the question remains open. Our motion through the universe is real, measurable, confirmed by multiple independent lines of evidence. We are moving toward the Great Attractor at roughly 600 kilometers per second. We are being drawn, along with the entire Laniakea Supercluster, toward a convergence basin that corresponds to one of the densest regions in our cosmic neighborhood. We are simultaneously moving away from a vast void in the opposite direction. And all of this is happening within an expanding universe that will, in the very far future, carry the Great Attractor itself beyond the reach of any gravitational connection. The drift is real. The destination is uncertain. The forces shaping our path are still being mapped. And through all of it, through the surveys and the simulations, through the decades of careful observation, through the slow accumulation of understanding, the universe itself remains indifferent to being understood. The dipole repeller does not know it has been named. The Shapley supercluster does not know it is being measured. The filaments of the cosmic web do not know they are being traced. They simply are. Vast and quiet and continuing. As you are continuing now, breathing slowly, the weight of the day already distant, the questions of any single life already softening at the edges. You are part of this motion too. Every atom in your body is moving with the Milky Way, carried along the same gravitational streams, drifting in the same direction as 100 billion other suns. You are not separate from the universe that is being described. You are inside it, resting inside it, moving with it, even now, even in stillness. The Great Attractor is 250 million light-years away, and the distance between waking and sleep is much smaller than that. So the motion is not simple. It never was. There is no single hand pulling the Milky Way through space. There are many, a whole surrounding architecture of mass and emptiness, each part contributing its quiet pressure. The Great Attractor draws us forward, and from the opposite direction, the vast hollow of the dipole repeller eases us along, not pulling. Exactly, but offering less resistance, less gravity to hold us back. So we drift, the way a leaf on still water drifts, not because something is dragging it, but because the surface itself is uneven. This is what the full picture looks like, as far as we can tell. Our motion through the universe is shaped by everything around us, by the dense nodes where matter has gathered over billions of years, and by the voids where it has not, by the filaments threading between clusters, and by the wide, near empty spaces that make up most of the volume of everything that exists. It is the whole structure, taken together, that determines where we are going. No single attractor tells the whole story. And that structure, the cosmic web, the filaments, the voids, the slow gravitational rivers flowing toward convergence, that structure is not permanent. Nothing at this scale is permanent. The universe is expanding, and the expansion is not slowing down. It is accelerating, quietly, steadily, without announcement. Space itself is stretching, and it has been stretching since long before any eye existed to notice it. At small scales, gravity holds things together. The Milky Way will not be torn apart. The Norma Cluster will not dissolve. Local gravity is strong enough to keep bound things bound. But at larger scales, the expansion wins. Galaxies that are far enough away are already receding faster than light can cross the growing distance between us. Not because they are moving through space at impossible speeds, but because the space between us is itself increasing, stretching the distance faster than anything can travel across it. Those galaxies are not gone, but they are, in a meaningful sense, already unreachable. And over time, more will join them. In the very far future, across timescales so long they have no comfortable human name, the accelerating expansion will draw galaxy clusters apart from one another. The gravitational streams that today connect Laniakea, that flow toward the Great Attractor, that link our local universe into something coherent and mappable. Those streams will fade, the flows will slow, and eventually they will end. Not because the Great Attractor disappears. It will still be there, still massive, still the gravitational heart of a vast region of space. But the space between here and there will have grown too wide. The pole will still exist, but the distance will have outpaced it. The Milky Way, or whatever remains of it by then, will simply no longer be close enough to feel the tug. The Great Attractor will become unreachable the way a shore becomes unreachable when the current is stronger than any stroke. You do not stop existing. The shore does not stop existing. The distance simply becomes final. And in that far future, each cluster of galaxies will be an island, surrounded by an expanding emptiness that grows faster than light, unable to see what lies beyond its own gravitational neighborhood. The cosmic web, which took billions of years to form from the faintest quantum whispers in the early universe, will have been undone by the same expansion that once allowed it to grow. But that is not now. Now, the drift continues. Quiet, vast, and entirely indifferent to the passage of any individual life. The Great Attractor does not know that civilizations have risen and fallen in the time it took light to cross a fraction of the distance between here and there. It does not register the centuries that astronomers spent learning to read the sky. It does not slow for grief or quicken for joy. It simply exerts its pull, as it has for hundreds of millions of years, as it will for hundreds of millions more. The drift is not cruel in its indifference. It is simply what it is. And there is something restful in that. To know that the largest forces in the universe are not watching, not measuring you, not waiting for anything from you. The gravitational streams do not require your participation. The cosmic web does not need to be understood to continue its slow geometry. You are carried along regardless, an atom among atoms, a life among lives, a moment inside a motion so large it has no edges you could ever reach. Even now, lying still, even in the quiet of this moment, with your breath slowing and the edges of thought beginning to soften, you are moving. The Milky Way carries you at roughly 600 kilometers every second toward a region of space 250 million light years away. Your stillness is only stillness relative to the ground beneath you, relative to this room, relative to the small, familiar world that holds you tonight. Relative to the universe, you are in motion. You have always been in motion. Every night of your life, every moment of sleep, every dream, all of it has taken place inside a universe that was drifting, flowing, expanding, continuing. You were never truly still. You were resting inside a motion too large to feel. And perhaps that is enough to know. Perhaps it is even a kind of comfort that the universe does not ask you to hold it together, that the filaments will continue without your attention, that the Norma Cluster will go on accreting galaxies whether or not anyone is awake to think about it, that the light which left those distant stars 250 million years ago is still traveling, still crossing the dark, still arriving, and will arrive whether you are watching or not. You can let go of the watching. The universe continues. The drift continues. And you are already somewhere between waking and wherever sleep takes you. the thoughts loosening their hold, the body settling deeper into the quiet. Somewhere, 100 billion suns are moving through the dark. Somewhere, the light from the Norma Cluster is crossing a distance that has no name in any human language. Somewhere, the cosmic web holds its slow shape, filament by filament, void by void. And here, there is only the breath. In and out. The universe is large, and you are small within it. And that is all right. That has always been all right. The drift goes on.